I just want to go quickly over what was the last thing that we had done during the previous session, which was some consequences of the center of gravity and what connection is there between the center of gravity and stability of an object. Okay, so the connection between center of gravity and stability we examined by looking at the following. That is, I'll take a slightly different example from the one I took last time. So if you take an object like a rectangular cuboid, okay, uniform sides, right? Now you can say that the center of gravity sort of lies somewhere there, right? So that will be the center of gravity. Now the question is, um, what determines the stability of an object like this? Say if you try to rotate it about this axis. Okay, so what we saw was that, well, the extent to which you can lift this object, tilt this object before it falls over, is when the line of action of the gravity, okay, the mg, the weight of the object, acts through the base of that object, right? Now obviously you can tilt this object, sort of trying to see if I can maintain that proportion. Okay, to the point where obviously the line of action of the force, wait, let me, right, remains within the base. So that's the maximum to which you can tilt this object, right? Before you go to a point, if you tilt it any further, okay, so let me just show it as if it's been kind of lifted up, right? And if you push it anywhere beyond that, then the line of action of the force shifts beyond the base. Then obviously it's not going to fall backwards, it's going to topple over. So it's going to tilt over, right? If you then think about doing it the other way, the mirror image of it. So if you tip it this way, the same thing will happen, right? The center of gravity, you can move it all the way to the point. Oh God, do I have to draw the whole thing again? Looks like I do. Okay, so you have the center of gravity. Let me cook it up a little bit. Put the center of gravity there, mg, right? So you have tipped it over in this direction now. Oh, they look the same. I should have used the same thing. Okay. So the obviously the angle through which you can actually tip this object is this, right? Before it will topple over. If you tip it to an angle within this and then you let it go, the object will obviously then fall back uh, into the base. Okay, so it's stable within the base. The moment you go beyond the base, you tilt it in such a way that the weight of the object, that is the gravitational force acting on it, goes beyond the base, then the object will tip over. Now the same object, of course, you can also turn it around to its side, yeah, like this. Yeah, like that. All right, and then the center of gravity still remains here, but I can't show it in 3 dimensions anymore, so I'll just show it in 2 dimensions, right? The center of gravity is somewhere thereabouts. Okay, now obviously the angle through which you can tip it without it collapsing has considerably reduced to that much. So you can tilt it this way, you can tilt it that way. The angle through which you can tilt it is only that much, and then it will collapse through that. So this was kind of a quick recap of what stability in that manner is. So, and then there are some curious sort of cases of an object center of gravity and consequently its stability. The one case that we were looking at is the donut, right? Is it necessary for the center of gravity of an object to be within its body itself? Well, it turns
No,
out that
sir.
it's not. Yeah, sorry. It's Seth, you want to say something?
A question.
Yes, please go ahead.
What is the fine difference between COG and COM?
Okay. I was afraid somebody is going to ask that question. Okay, so there are two terms technically. One is the center, I keep writing RE, center of uh, gravity, which is what we are studying now. And then there is another term, center of mass. Okay, and strictly speaking, as of now, these two phrases can be used interchangeably. Okay, so they essentially mean the same thing. But of course, you have to ask the question, well, um, if there are two different phrases, then there must be two different things. Why should there be two different phrases for this? Or is there some kind of an historical anomaly or something? That's often the case. Um,
Arun sir,
yeah,
sir, as Janvi said that it might vary, something like that.
yeah, I'm
On
just
Earth,
coming
it
to
will
that.
be the same. So
Yeah,
I
I'm just
think that
coming to that.
center of gravity, I
Yeah.
think that center of gravity will vary from object on object, like in space. Like if you take the moon and the
Mhm.
Earth, it will be different on both. But center of mass won't be because the mass is the same.
Correct. Okay. Yeah. So you kind of put it in the ballpark. That's right. The center of mass and the center of gravity can be said to be more or less the same thing for objects on Earth which are considerably smaller in mass to comparison with the Earth. So for small objects on Earth, the center of mass, the center of gravity doesn't really matter. But the moment the object that you are considering starts becoming comparable in mass to the Earth, right? Because we are looking at the center of gravity from the aspect of the gravitational pull, right? We have actually defined it in such a manner that there will be no torque about that imaginary point. But if the size of the object becomes considerably larger and comparable, I don't know what is the limit of that comparison, but comparable to the size of the Earth, then yes, the center of mass and the center of gravity start becoming significantly. The differences start becoming significant. Okay, so as
Like
of now,
Mount.
let's not. No, I would imagine that yeah, maybe a mountain the size of Mount Everest. Yeah, there I think that there might be a discernibly small difference between the center of gravity and center of mass. So I'll leave it at that. Maybe I can share something a little later which gives you a better picture of what is the difference between the two. So right, as of now, so as not to confuse anybody, the center of gravity and the center of mass, we can keep it as the same. We will henceforth refer to it as center of gravity alone. Although here and there in my classes, I do tend to say center of mass instead of center of gravity. That's just a mistake. I should just be saying center of gravity. Okay, so as not to confuse everybody. So coming back to our question about does the center of gravity of an object have to be on the body itself? Well, no, not necessary. As can be seen in the case of a ring or a toroid or a donut, the center of mass or the center of gravity of the object, right, lies in space. Okay, because that is the only place about which the mass distribution is equal in such a manner that there will be no torque. So if you throw a ring up, right, I don't know if you people have played with these rubber rings that used to be. I mean, that there was a game that we used to play with the ring, throwing the ring and catching. I don't know if you people, anybody has played that, but anybody who played with even a kind of an finger ring or something, or a bangle, right? You'll know that if you toss the ring up, it spins, right? So it undergoes rotational motion. The rotational motion, if you see carefully, spins about where, right? It spins about this axis. So if you look at it kind of sideways, right? If you spun this uh, object, like give it a spin and move it in the air, or if it's a smooth object, you spin it on the ground, then you'll find that the axis of rotation actually neatly passes through the center like this. Okay, and it is around this axis that the object happens to be spinning. Okay, so that's one indication that the center of mass of the object is over there, because when you spin an object, it is around the center of mass that there is no noticeable torque that is there. You have provided an external force to spin it around, so it will spin about that axis. Another thing is that when you suspend a ring or a donut or a toroid, right, it gets suspended like that, right? So the gravitational force from the center of gravity is obviously acting in this direction, right? And the tension which is providing the support is acting in the other direction. So which means that the line of action of the force passes through the center of mass. So therefore it is supporting that center of mass. And the third example is, if you have a ring and you place it on the ground like so, right? Again, the center of mass is there, which means the gravity is acting this way and the support force is acting at the same spot, of course. I'm just showing it slightly different, but it's acting in the same spot in the upward direction. All right. Okay. Okay, so that's, these are all different ways of showing that the center of gravity of such an object indeed lies at the center where there absolutely is no mass. Okay, so this is one curious situation, and of course that's also true for an object like a hollow sphere. If you take a hollow sphere, so it's a sphere with some thickness. Excuse me. No, I don't have corona. Okay, there's some thickness to it, but it's hollow inside. Nevertheless, the center of gravity of the object will lie right through the center. And it becomes very interesting to consider that when a ring or a sphere, like a ball, you see, if you roll it, then what happens to its stability, right? Could somebody make a statement for that? What can you say in terms of the stability of an object like a ring or a sphere? Yeah, Akshay is saying it doesn't change. What doesn't change? We can see that arguably something like a ball is very, very stable, in the sense that you can't really topple it. You can't talk in terms of toppling an object like a ball. Why is that so? Yes, the line of action of force. Yes, whatever you do, when you rotate the object, when you spin the object, when you make it roll along the floor or the ground, the line of action of force is always through its base. It never changes. So since the line of action of force is always through the base, it's stable at all times. Okay. And then we come to another curiosity. I don't know if you people have seen this. It's a kind of a toy that you see in toy stores, and it kind of looks somewhat like this. It's fairly big. This height can be what, let's say about something like 4 feet. Okay. And what happens is, if you give this guy a push, okay, what does it do if you give it a push?
It does not topple over.
Yeah, it doesn't topple over. So if you give this thing
back.
it comes back. Yeah. I'm glad some of
It
you have
has
at
a
least
weight.
It goes to the very end and it comes back.
yeah, so it kind of it can have some kind of a shape.
It has weight on the
Yeah, some kind of a dopey shape. So it kind of goes to one side, right, and then it comes back. It looks like if you give it enough of a push, it's going to topple and fall over, but it never does. You give it a push, and what it does, it goes to the side, and then it comes back on. Ever wondered how that happens? Yeah, and if you try to pick it up, right, you'll realize,
weight.
you'll realize that it has some heavy weight placed in the bottom. I don't know. I've never looked at what it was. I kind of assume that it is something like sand or
Sand.
sand or something like that, right? So when you push this over, no, sand would be a problem, right? Because what will happen is, if it is sand, then the sand will get distributed like that, and then it will just stay like that. But it doesn't, right? It's something that stays fixed in such a way that it's
put in
always
a
like this.
column.
Huh?
Put in a column. There's a partition at the bottom.
There is a partition at the bottom, so it cannot flow. If it's sand or something like that, it cannot flow. So then what happens is, because of this, the object seems to tip over, and then since the center of gravity is now acting just outside the base, what it does is it pulls it back. Okay. And then there is another one. This you might have seen in school also. There's all sorts of balancing toys, and one very good one involves a bird. It kind of looks like an eagle or something like that. I'll try to draw it as best as I can. Have you seen these ones? It's kind of like an eagle. It's a bad drawing of an eagle, but with its wings out in the front, right? And it looks like it can't balance on the beak over there, but it just about does. And no matter how hard, I mean, if you really give it a whack, of course it will fall off. Yeah, there is one outside the Tinker Shed. Yes, correct. Pallavi Akka made that. But it's balanced in such a way that if you tap it, it swivels about, it even turns around, but it doesn't fall off that easily. Okay, so all these are kind of consequences of where the center of gravity of the object is, and the fact that the object will be stable as long as you make it pass through its base. Okay, and that's how they create these kinds of curiosities. All right. So that's for center of gravity and stability.
So,
Yeah, go ahead.
you're saying that for like most normal objects,
Yeah.
they topple over when the center of gravity moves outside of them.
Yes, moves outside of the base, and it cannot be compensated by something like in the case of athletics and so on, dancing, athletics and so on. there may be moves that we make in which the center of gravity of our body, which essentially is somewhere around the navel. Okay, for men it's around the navel, and for women it is slightly below the navel. The center of mass shifts outside the base, but then we usually compensate it by increasing our rotational inertia. I mean, basically by putting mass out in such a way that we bring the rotational inertia again back within the base. So, was there any follow-up question to what you were asking?
Yeah, so what about torus?
What is that?
Torus, donut.
Yeah. What about it?
You said that
So the base. Okay. So if you look at, do you, well, the ring and the ball, I did discuss it. So as they rotate, what happens is that the center of gravity, the line of action of force of gravity on it, always falls on the base. So therefore, they just continue rotating. Are you talking about the situation of a, a torus like this?
a three-dimensional torus, sir.
Yeah. So this is three-dimensional, or the best that I can do three-dimensionally.
Sir, please don't joke. Even I can make better than that.
No. So what do you want to know?
Sir, what about a sphere, like a actual sphere in condition, like real life conditions? What happens? Is it possible for it to become unstable?
No, it cannot. That's what I said. A sphere just cannot become unstable, um, because the line of action of the force, even if it is spinning about or rotating, always falls on the base. Okay, you can ask the condition. So you can also actually think about a situation like this. What if there is a slope, right? And now you can say that, well, the reason why a ball goes down a slope is also because it's trying to find stability or a place where the line of action of force of gravity falls within its base, right? How will it become straight again? You mean the sphere or the torus? Oh, the toy thing, you're still there. The same argument. What will happen is when you tilt the toy, what happens is that the center of the line of action of the force is always acting towards the center of the earth. The base has now moved in such a way that the line of action of the force and the base are not at the same place. So what it will attempt to do is it will attempt to rotate in such a way that the line of action of the force and the base coincide again. Yeah.
Sir, they're asking what if you like topple over, like you tilt the toy.
You tilt the toy in the sense you just can't tilt it. That's the whole point.
No, sir, you lift it and put it upside down.
No, you can't put it upside down. Upside down, it's not balanced. You mean to say you'll put the toy like this? It will come back. No, it will fall back. There will be some torque unless you balance it. Let's say you take it even to the extreme position, like this, right? So now what's happening is that the center of gravity of this toy is, like, say, somewhere there, and the line of action of force is here. So it's this kind of a situation. So what will happen is there is going to be, this is the point of contact, right? So that is the axis of rotation. So now there is going to be a clockwise torque on this object. So because there is a clockwise torque, it will start turning. So it will turn, come back to its stable position. Okay, and set, did I get the did I kind of ballpark answer your question?
Yeah, like, but the answer is not satisfactory. Like, I still think a sphere
Sphere can?
can become unstable.
Mm, no, I mean, you will have to then define what is instability. And instability would be a point where the center of gravity, no, the center of the line of action of force and the point of contact, the base of the object, are not coincident. So then it becomes unstable, which means it can topple. And talking about toppling of a sphere is somewhat contradictory, right? You can't topple a sphere, which means that you can't make the line of action of gravity go beyond its base without it trying to straighten itself out again. Okay, so anyway, you give it some thought. You see if you can understand this. Okay, there is just one more small thing that I wanted to mention, and we can stop right after that. It's a very interesting consequence. When athletes do this high jump, right? Now, what you would normally say is that, well, if an athlete is doing a high jump, uh, and I hope you people know what I'm talking about when I say a high jump, right? So it's not a pole vault, not by using a pole. So you just come running and you jump over a barrier. So you'd say that, well, the athlete would have to carry his center of gravity, his or her center of gravity, over the bar in order to make the jump, right? So you'd say that that has to be done. The center of gravity of the athlete has to go over the bar. Yeah, and not really.
No, sir.
Set and Janu.
Even
Yeah.
even when we try to go over the fence,
Yeah.
We raise our legs, we hop over the fence, but our center of gravity doesn't go up by that same amount.
No,
There
I'm
is
not talking
more
about the same. No, yeah, that we did the experiment with the hang time experiment, and we realized that. What I'm saying is, when you go over the fence, right? Does your center of mass or center of gravity, sorry, also go over the fence? I'm not saying how high it goes.
I do not think that is necessary.
That may not be so, but not from the example that you are giving.
Yeah, like.
So to come to Janvi, you wanted to say something. Yeah, you're saying maybe not. Yeah, you're both right. It's not necessary that the center of gravity go over the bar when somebody is doing a high jump or even a pole vault for that instance. But how is that possible? Okay, it is possible if you take that as being the bar as seen from the sideways, right? So an athlete who is trying to, so I'm going to kind of draw a rough diagram of an athlete trying to jump over the bar. Okay.
Sir, no offense meant, but that looks like a dog stretching itself.
Yeah, it's okay. I don't mind the offense. You begin making diagrams better than mine, then I will consider your comments. So there are different ways in which it can be done. One is the old method. I think this was just when you try to run in and then you jump straight ahead with your toes pointing forward. Okay, so this is the pole. Okay, and you have the cushion over there, so you land on the cushion. Now, in this case, the supposedly the athlete's center of gravity is over there, and it clearly goes over the bar. Okay. Now, at that kind of a height, to push your center of gravity over the bar, requires quite a lot of effort. In fact, what you would like to do is you'd like to just about make the center of gravity go over the bar, which means if you are actually doing the center of gravity is over there and you are pushing it over the bar, that means that you can actually, strictly speaking, take the bar that much higher, because what you need is the center of mass to go over it. Are you kind of understanding the? Yeah, he's jumping over the pole. Yes. Okay. So what the athletes develop is a kind of a leap called a Flossberry flop. I guess it was done by an athlete called Flossberry. Okay.
It was done
In
by a man called Richard Flossberry.
Richard Flossberry, very good. Thank you. In which I don't know if he used the principles of center of gravity and so on and toroids to actually figure this out. But what he figured out was if he curled his body tightly enough, okay, and he realized that you can't do that when you jump like this, you will have to do that when you jump backwards. Okay, so what he did was he realized that if you kind of made your body into a ring like structure, right, then the center of the gravity of the ring can be way lower, right, because that would essentially fall somewhere over here, right, while the rest of your body can actually go over the top. Okay, so what he figured out, of course you can't make your body into a ring, you can't at least contort yourself into that much of a shape. So what he figured out was, well, if you can just about uh, contort your body in such a manner, and I'm kind of going to change the shape shift a little bit of this, and let's say that's him, right, and that's a Flossberry flop. What he can do is, then of course your center of mass is not going to be there, it's going to shift a little bit higher than that. But what you essentially do is you make the center of mass of your body go below the bar while the rest of the body can go over it. What good that does that do is it increases the height that you can jump, because you don't really need to push your center of mass over the bar. All you need to do is make the center of mass go just below the bar, because it can lie outside the body, but the rest of the mass of the body can move over just momentarily at that point of time when you are going over the bar, and then you lift your legs up as you pass the bar, and then you make it out. So if you look at some of the videos that are there in YouTube, they actually place a camera along the bar over there, and they have slow motion shot, 1000 frames per second shots that actually show how this is actually done by athletes. Okay, so it kind of pushes the boundaries of how high you can jump, because you don't really need to put your center of mass over the bar. Okay, and Akshay found out it's Dick Fosbury, not Richard Fosbury. Well, and with 1 hour, not 2 hours. All right, so much for center of gravity and pushing the body over the bar. So I'll probably have to create some kind of an assignment for you people over what concepts we have covered at this point of time, and we'll do that in a bit. So I guess we'll meet again on Thursday. Ratul saying again that it's Richard. Well, anyway, it doesn't matter as long as it's Fosbury, and the jump is called the Fosbury flop. Okay, any questions from anybody? Anything that we have
Arun,
discussed
sir?
today? Yeah, go ahead.
2 questions.
Sure.
Will we be covering gravity as well?
Yeah, my aim is we will do. Now we are almost at the end of this chapter, rotational motion. I need to do a small bit about rotational momentum, angular momentum. Once angular momentum is done, then we will go into gravity and then into satellite and projectile motion.
And what about those modern physics classes, the brief history of time.
Just the reading sessions. Yeah, I haven't yet taken a call on that. I'll probably send you people a form because I want to know what will be an optimal time for us to meet. So that I will. I'll also send a form for that. So I have a assignment that will come through maybe today or tomorrow, and also a form for those people who opted for the reading sessions, so that we can fix some kind of a time and sequence for that. So those two things are still pending. Yeah. Anything else?
No.
And the third point is that you people should try out the experiment, the uniform lamina experiment. Please take pictures. I will also share with you some way in which you can upload the photographs to the Google Classroom. Okay,
You
so
also
so
try
three things are
Fosbury
pending.
flop, no?
I have what?
Why don't you try the Fosbury flop?
Yes, when I used to do the high jump, I used to use the Frostberry flop. I didn't have
Sir,
a great jump, but I have tried it. Yeah,
sir, one more doubt. Like, in the case of the sphere,
yeah, yeah.
the angle which you were telling for the equilibrium to be, like, I mean, stable.
Yeah.
Are you like? Do you mean that for a sphere that angle is 360 degrees? Like,
Yeah, that's an interesting question. You could say it's zero, or you could say it's 360 degrees.